Happy to be back in another episode of Environmental Digest, and today we're going to talk about one of the biggest, most persistent global challenges, cleaning up our water. Specifically, how these emerging hybrid technologies are tackling the invisible poisons that traditional wastewater methods just miss entirely.
That really is the core issue, isn't it? When we think of water treatment, we usually picture filters removing sludge or sediment,
Right, the big stuff.
the big stuff.
Yeah.
And those conventional techniques, filtration, sedimentation, even simple chlorination, they're essential for solids, but they utterly fail against what are known as recalcitrant organic contaminants.
That phrase, it sounds just as stubborn as the pollutants themselves. What are we actually talking about here?
Well, we mean pollutants that are incredibly difficult to break down chemically. Think of the complex structures you find in persistent pharmaceuticals, certain industrial dyes, or even pesticide residues.
Ah, so the things that just dissolve and stay in the water.
Exactly. They remain dissolved even after all the standard processes, and they're just incredibly difficult to remove or degrade using those conventional methods.
And often when we try to use, traditional chemical fixes like massive doses of chlorine, we just end up creating one problem for another, right?
Absolutely. Traditional chlorination especially can react with other organic matter that's just naturally present and create these harmful disinfection byproducts.
Like trihalomethanes.
Specifically compounds like trihalomethanes, which pose definite risks to human health and the environment. We need something that doesn't just move the pollutant around, but actually destroys it, breaks it down into harmless components.
So we need chemical wrecking balls, not just sticky notes.
Exactly. And that is the realm of advanced oxidation processes, or AOPs. The fundamental goal of any AOP is to generate highly reactive species. And the chief among them are what we call hydroxyl radicals. These radicals are incredibly short-lived and just immensely powerful. They attack nearly any organic molecule and rapidly degrade those persistent structures into, ideally, just water and carbon dioxide.
And the star of our deep dive today is a powerful hybrid AOP, sonophotocatalysis, or SPC. This is a brilliant synergistic concept that essentially leverages two universal free resources, sound and light, specifically solar energy.
And our mission today is to really understand the engineering elegance of this combination. We need to unpack the synergistic mechanisms that make it so efficient, figure out the critical parameters for optimization, and, ultimately determine if it can be economically feasible for massive real-world adoption.
The idea of using sunlight and sound waves to break down super tough industrial waste, it sounds almost like science fiction. Let's start with the basics. Okay, so let's look at the individual components that make up SPC. What's happening, mechanically and chemically when you just apply solar energy for water cleaning, and then what happens when you hit it with ultrasound.
Let's start with the light, solar photocatalysis. This process requires a semiconductor catalyst, typically something like titanium dioxide, which acts as the chemical engine.
Okay.
When this catalyst is exposed to sunlight, the energy excites the electrons inside the material, and this generates pairs of electrons and holes. These pairs then move to the surface and react with water or oxygen to form those critical hydroxyl radicals we need.
It sounds beautiful in theory, but I know it runs into some pretty big real-world issues. What are the main limitations of just using light-driven cleaning on its own?
There are a couple of major hurdles that really slow the whole process down. First, there's an efficiency issue. Most common catalysts, like the one I just mentioned, they require high-energy UV light to get excited. Engineers call this a large band gap.
So if we're using artificial UV lamps, that gets expensive and energy intensive.
Very. And while using the sun helps, the system is much less efficient in the visible light spectrum.
So we're asking for sunlight, but the engine is really only geared for UV, which is just a tiny fraction of the whole solar spectrum.
Precisely. And the second major problem is a physical one that limits the treatment rate. Mass transfer resistance.
A traffic jam.
It's a traffic jam, exactly. Imagine the catalyst surface is a chemical toll booth, ready to process pollutants. If the water is just sitting there, the pollutant molecules have to passively drift over to the surface, and that slows everything down.
Okay, that makes sense.
And this traffic jam not only prevents the pollutant from reaching the active sites, it can also lead to the catalyst surface getting dirty or, deactivated over time.
Right. Now let's bring in the second component, sound. How does sonocatalysis work, and can it fix that traffic jam?
Sonocatalysis uses high-frequency ultrasound. We're talking frequencies far beyond human hearing, generally between 16 kilohertz and 1 megahertz. This sound energy creates and then violently collapses tiny vapor bubbles. The process is known as cavitation.
That implosion must be incredibly intense.
It is. When these bubbles collapse, they create these highly localized hotspots. We're talking temperatures reaching thousands of degrees, immense pressure.
Wow.
This physical violence alone generates hydroxyl radicals directly in the water. But the crucial insight for our combined system is that this intense, violent implosion also generates light. It's a phenomenon called sonoluminescence.
Wait. The sound creates light.
Yes, it's like a tiny, high-energy internal flashbulb going off over and over. And here's where the link happens. This light that's emitted by the collapsing bubble is energetic enough to excite the semiconductor catalyst, mimicking the effect of high-energy UV light.
So the sound provides both a chemical cleaning effect and a light source to boost the catalyst.
You've got it. It's doing double duty.
So we've established the two building blocks, but the real game changer here is what happens when you put them together into SPC. How does one process actively boost the other beyond just, simple addition?
Well, we're looking for true chemical symbiosis. The combination is specifically designed to attack the fundamental weaknesses of the individual processes at the same time. It creates leverage.
Tell us about that leverage. We talked about mass transfer, the traffic jam. How does the sound solve that?
The acoustic energy from the ultrasound creates this intense local turbulence and rapid fluid movement. It's called acoustic streaming.
So it's like having a powerful chemical agitator built right into the system.
That's a perfect way to put it. This turbulence dramatically enhances the mass transfer of pollutants, forcing them out of the bulk liquid and onto the catalyst surface much, much faster than just passive drifting.
So the sound is actively delivering the pollutants to the light-activated sites.
Exactly. And that turbulence is doing double duty. It's also continuously cleaning the catalyst surface. It prevents the particles from clumping up, from agglomerating, and it clears off any reaction intermediates that might deactivate the site.
So it keeps the toll booth open for business?
It keeps it wide open, ensuring the maximum surface area is always ready for a reaction.
That's a huge physical benefit. But what about the chemistry inside the catalyst itself? You mentioned that the electron and the hole can just recombine and waste energy if they don't react quickly. Does the sound help there too?
It does. And this is a vital chemical enhancement. The ultrasonication helps to physically separate the photogenerated electron-hole pairs within the catalyst.
Okay.
And that separation is key, because if the electron and hole meet and recombine, they just release their energy as heat. No useful hydroxyl radicals are produced. By promoting separation, SBC ensures a much larger percentage of those pairs actually go on to generate the radicals we want.
So the light creates the energy, and the sound acts as a kind of chemical traffic cop, making sure that energy is used for cleaning and not just wasted as heat. This truly sounds like the whole is greater than the sum of its parts.
And we can actually quantify this. We can measure this synergistic leverage using something called the synergistic index. If that index value is greater than 1, we have mathematically proven that the combined process is more efficient than just adding the outputs of the two separate processes together.
Give us an aha moment example from the research. Show us this multiplication in action.
The results can be dramatic. Studies that were looking at the degradation of a common industrial dye, rhodamin B, they reported a synergistic index of around 2.14.
So more than double the performance.
More than double what you'd expect. But the real breakthrough comes in examples like the degradation of methyl blue, where the rate was reported to be 56-fold higher when using sonophotocatalysis compared to photocatalysis alone.
56 times faster. That is the kind of performance multiplication that completely changes the economic feasibility of an entire system. Okay, so if we were actually operating one of these high-tech water treatment plants, we need to know where the control knobs are. What are the key operational parameters we would have to tune to achieve these maximum synergistic gains?
Optimization is everything in AOPs. There are really 4 parameters that dictate success, and the first is perhaps the most chemically critical: pH.
If we're pushing this to an industrial scale, we're talking about massive volumes of water. If the best treatment requires a really low pH, that sounds expensive and potentially corrosive for the equipment. Is there a point where you have to trade off that peak performance for feasibility?
That's a necessary engineering challenge to consider, for sure. But chemically, the acidic environment is pretty non-negotiable for maximum efficiency. Low pH heavily influences the charge of the catalyst surface, the pollutant absorption, and critically, the oxidation potential of the radicals.
Meaning they're just stronger.
Simply put, the hydroxyl radicals are far more powerful in acidic conditions.
And do the numbers really confirm that drastic a difference?
They absolutely do. One study on a specific industrial dye, Direct Blue 71, achieved a complete 100% degradation when the solution was maintained at a pH of 2.5.
Wow.
However, when the pH was raised just slightly to 5.5, which is still acidic, mind you, the effectiveness plummeted to only 29%.
That's a staggering drop-off.
It is. Likewise, phenol removal effectiveness dropped from 85% in acidic conditions to 60% in alkaline solutions. You just can't ignore the charge game.
Okay, lesson learned. We need that acidic environment for maximum power. What about the actual concentration of the contaminants we're trying to clean?
That's our second key knob, pollutant concentration. You need an optimal sort of Goldilocks zone. If the concentration is too high, two bad things happen. First, the pollutant molecules start competing with each other, scavenging the radicals before they can complete the breakdown.
Okay.
And second, the high concentration actually hinders light penetration, which slows the photocatalysis part down.
And what if it's too low?
Paradoxically, if the concentration is too low, the highly reactive radicals might just start reacting with each other instead of attacking the contaminants, which again reduces the effective treatment rate. You need enough contaminant there to give the radicals a target.
And the research must have a perfect example of this concentration trade-off.
Oh yes. For a common dye called rhodamine B, complete degradation was achieved in just 10 minutes when the concentration was at 2.5 parts per million.
10 minutes, that's fast.
But when they doubled the concentration to 5 parts per million, it took 35 minutes, so more than 3 times as long, to achieve the same result. The economic implications for treatment time are huge based on concentration alone.
What's our third tuning knob?
Catalyst loading, and this is the classic, more is not always better problem. Increasing the catalyst loading does increase the number of active sites, which is good.
But there's a catch.
There's a catch. If you load too much, the particles start to aggregate, clump together, which actually reduces the available surface area. And crucially, too much material begins to scatter both the solar and the ultrasonic energy, preventing it from reaching the reaction sites.
So you have to find that sweet spot.
You have to find that specific sweet spot that maximizes surface area without interfering with energy delivery.
And finally, the input energy itself, the sound waves. What do we need to know about optimizing the frequency and power?
Ultrasound power and frequency. Generally, higher power enhances cavitation and mass transfer, which we love. But if the power is excessive, you run into something called a cushioning effect.
That sounds like too many pillows. What is it chemically?
That's a good analogy. Too many cavities form in the liquid, and they start acting like a cushion, dampening the intensity and the force of the collapse of the other bubbles. You lose that extreme energy needed for radical generation, and you end up just wasting electricity.
I see. And what about frequency?
As for frequency, lower frequencies, between 20 and 100 kilohertz, are generally preferred for SPC. This range tends to produce the larger, more powerful physical effects of cavitation that are necessary to drive that synergistic interaction we talked about.
Okay, moving from these operational parameters to the actual hardware scaling this up requires the core components to be robust and effective in a real-world environment. How are researchers modifying the catalysts so they become truly solar-driven rather than just relying on that high-energy UV light?
This is where innovation is absolutely critical. Since common catalysts are, chemically designed to absorb UV light, we need to fundamentally change their structure to respond to the much more abundant visible light spectrum. There are 2 main strategies being deployed.
Let's start with the first one.
The first is doping. This is like adding a tiny controlled impurity, usually small amounts of metal or non-metal dopants, like introducing a bit of iron into a zinc oxide catalyst.
And what does that do?
This microscopic change lowers the catalyst's inherent energy barrier, that band gap, allowing it to get excited by the gentler visible light. We are essentially hacking the catalyst.
Turning it from a UV-only camera into one that can use the full spectrum of solar power.
That's the goal, making it a true, cost-effective, solar-driven technology. And the second strategy involves coupling nanomaterials to create what are called heterojunctions.
Okay, what are those?
This means combining 2 different nanoscale semiconductors. When you do this, you establish an internal electric field right at the junction point between them.
And what does that internal electric field do?
It acts as an internal traffic cop. It helps to physically sweep the electrons and holes away from each other, preventing their rapid recombination. This significantly enhances the stability and the overall radical generation efficiency because the charges are now separated and ready to react.
So on the engineering side, we're moving from the beaker in the lab to large-scale continuous flow systems. What challenges does reactor design present?
The core challenge is uniformity. For industrial-scale wastewater processing, we absolutely need continuous flow reactors, not little batch systems.
Right.
And the design must ensure that the thousands of gallons passing through receive uniform exposure to both light and sound. For the solar component, this might involve complex arrays using parabolic reflectors to maximize light capture.
And for the sound,
For the ultrasound, it means moving far beyond a single submerged probe. Instead, you'd use multiple high-power, multi-frequency transducers that are strategically placed throughout the entire reactor volume.
ultimately, the most important metric for adoption outside of performance is cost. Is sonophotocatalysis merely a powerful lab curiosity, or does the synergy actually make it economically viable?
This is probably the most compelling finding in the research. While the technology is highly effective at breaking down these persistent pollutants, the efficiency gains translate directly and powerfully into cost savings. SPC is shown to be significantly more cost-effective than either individual method.
That's a critical point. Can we see the evidence for that? Can you provide a cost comparison for achieving the same level of cleanup?
Certainly. One detailed cost assessment study looked at the resources required for 90% elimination of a reactive azo dye. The estimated total costs for sonolysis alone were significant, totaling over $4,200 per unit volume.
Okay, very expensive.
Photocatalysis alone was much cheaper, but still cost over $739 per unit volume.
And the hybrid approach.
The combined sonophotocatalytic process drastically reduced that cost, coming in at only $234 per unit volume.
That is a staggering reduction, moving from thousands to just a few hundred for the same amount of cleanup. That proves the economic case for synergy. It's not just chemically better, it's radically cheaper because it uses less energy and time to get the job done.
Precisely. That economic leverage is the powerful driver that should accelerate its widespread adoption in the coming years.
So, to summarize the key takeaway from this deep dive, sonophotocatalysis is an elegant and powerful synergistic technology. It combines high-frequency sound and solar energy to generate those highly reactive hydroxyl radicals, giving us a mechanism to destroy persistent organic pollutants that conventional methods just can't touch.
And for any engineer or operator looking to implement this, the secret to maximizing that value lies in precision tuning. Maintaining that acidic pH for maximum radical potential, ensuring proper pollutant loading to avoid chemical self-sabotage, and utilizing these specially modified catalysts that can absorb visible light.
And of course, precisely balancing the ultrasound power and frequency to achieve that peak physical synergy. But despite the tremendous performance and the clear economic advantage, what are the final roadblocks before we see this widely implemented in major municipal or industrial treatment facilities?
The major challenges are largely focused on future stability and energy demand. We still need to engineer the next generation of catalysts that can utilize even lower energy light down into the near-infrared spectrum to get maximum solar harvesting.
Right.
We also need to guarantee the long-term, multi-year stability and reusability of these catalysts within continuous flow industrial reactors. And plus, while the efficiency is fantastic, the current electricity demand needed to run the powerful sonication component still needs optimization to truly maximize the overall benefit.
This research really highlights the critical need for continued investigation into energy-efficient, continuous flow pilot-scale reactors. If this hybrid technology can be fully scaled up and we can maintain that enhanced pollutant elimination while drastically reducing the cost per unit of water, how might this fundamentally reshape water management practices in rapidly urbanizing sunny regions of the world? It could mean the difference between having safe water and not.
It raises the crucial question of accessibility. If this technology delivers clean water at a tenth of the cost of current advanced methods, what new possibilities does that unlock for water security globally? That is the scale of the change we're talking about.